Okay, hi everyone. Thanks for coming along today to this seminar, this expert talk from Dr. Ashley Hood. I'd just like to begin by acknowledging that this webinar is taking place on the lands of the Wurundjeri people and to pay my respects to their elders past and present, and also to welcome any Indigenous people to this webinar. So this webinar is the expert talk for the discovery subject. So there will be an assignment related to this talk, and I'll be posing that question later on this week, along with a rubric. So that will all become clearer soon. The assignment will be due in week 8, so in about a month's time, roughly. So thank you all for coming. I'll just introduce Dr. Ashley Hood. Ashley is a senior lecturer and Australian Research Council funded research fellow in the School of Geography, Earth and Atmospheric Sciences at the University of Melbourne. Ashley researches the long-term climate history of Earth and uses her geological background to try and understand long-term fluctuations in Earth's climates and place recent climate change in that context. So I'll hand over to Ashley. If you've got any questions, please put them in the Q&A. And we'll have some time for question and answer later on. Thanks.
Thanks very much, Andrew, and thank you everyone for coming. We're back online, but here we are. So today I wanted to share with you some of the really long-term controls on climate through Earth's history, through the billions of years of Earth's history. And hopefully the processes that shape this long-term climate, these geological processes, and the history of climate on Earth can really help to put our modern climate change in context. And so the idea, I'll just kind of give away the end right now, is that really if you look at the history of the Earth, there's really no time in Earth's history where our climate has changed as rapidly as it has today. And so I'm going to go through the controls on this climate history and then talk a little bit about some events that happened to put this in context. So first, I just thought I'd introduce myself. And what I do research on. I'm as Andrew said, I'm in the School of Geography, Earth and Atmospheric Scientist. I'm a geoscientist and I do a lot of field work and lab work to try and disentangle the Earth's climate history and environmental history and relate that to the evolution of life over billions of years in Earth's history. So I go to places like northern Canada, up in the mountains of the Yukon, and places like Central Australia. And I look at these rocks in detail and try to figure out what is happening with the climate and what is happening with life at particular points in Earth's history. And so one thing that I mainly look at is reef complexes. And so you can see this is a reef here, and this is a reef here. These are not in the water anymore, like the Great Barrier Reef. They're exposed up in mountain ranges and up made into rock. And I use these to determine, as I say, the history of life and the oceans through time. And when I started putting together this talk, I was looking for pictures on the internet of the Earth, and I came across this poster from NASA. So NASA created these vintage posters, vintage travel posters for the solar system. And this is the one for Earth, which I thought was really cool. There's a whole bunch of really cool ones, you know, the auroras of Jupiter and all this kind of stuff. But it struck me, this poster, because it's titled Earth, your oasis in space where the air is free and breathing is easy. And this is a really beautiful view of our planet. It's a really unique planet in terms of it's the only place we know that has life. It's had a stable climate, relatively speaking, through its history that's enabled life and liquid water to exist on the Earth through its long 4.5 billion year history. And we live on this planet where the air is free and breathing is easy. We have this atmosphere and biosphere and Earth that work together to control the stability of our planet and of our climate through time. So the Earth has not always looked exactly like this. It has gone through many stages in its history. And this image on the right just basically shows a very rough overview of that history. So we think the Earth is about 4.5 billion years old. And as we go around this circle, we move through time, billions of years up until today. We know that Earth has had water, liquid water on its surface for quite a long period of time. We think that life evolved. We have evidence for life at some point around 3.5 billion years ago. And these are things like cyanobacteria, microbial communities. There's a long period of Earth's history where not a huge amount happens. We get some oxygen in the atmosphere. Eukaryotes, or complex-celled animals, complex-celled organisms, evolve. It's not up until only relatively recently for a geologist, so 500 million years ago, that we have animals evolve. And it's only after that, about 400 million years ago, that land plants evolve. And humans, you can see, are so small on this timescale that they don't even get their own little bar. So this is a long history that Earth has had. And throughout this history, it's maintained a climate relatively stable enough for life to thrive. So it's not always looked like this beautiful planet that it looks like today. We've had many stages in Earth's history where we have a fundamentally different looking planet. And so way back in the early Earth, say 4 billion years ago in the Archean, this is an artist diagram of what the Earth might have looked like. And so the atmosphere at this time was thought to be very dense CO2 and methane, extreme greenhouse, which might have made the atmosphere appear orange, like Titan, like one of the moons in the solar system. Potentially there was organic haze raining out of the atmosphere as the sun hit this methane. There was no oxygen around. Our oceans were 100% anoxic, and they were full of things like dissolved iron, which would have made them green. And this is the Earth in which life first evolved, these microbial communities or stromatolites. And so even back in this kind of alien looking Earth, we had a climate that was warm enough and stable enough to support this liquid water. And so what I want to do in this talk is go through how its climate has changed over time and how we can record that in the rock record or in the long history of Earth's climates. So there are a number of different ways that we can record climate change in the past. And probably you're more familiar with human measurements, so the measurements that we make, or that we can look at, say, historical texts and figure out climate from these things. And these records go for hundreds or potentially thousands of years. And so here's Keeling. He's the son of the guy that did the Keeling curve, and he's measuring CO2 in the atmosphere. When we go back further in time, we have to sort of estimate the atmospheric composition or the past climates based on what we can find that records those climate conditions. So, for example, you might be familiar with tree rings that go back, say, thousands of years that record the seasonal variation of climates in a particular area. And then if we go even back further, we get to ice. So things like Antarctic ice cores, which go back up to several million years, but usually hundreds of thousands of years. And you can extract the little CO2 and atmospheric conditions out of the little bubbles trapped in the ice. But anything further back than this, the only record we really have of Earth's climate is sedimentary rocks, or the rock record. And this is an example of some rocks exposed. These go back millions and billions of years, and we can look at these changing layers of the rock as we go through time and tell a little bit about what's happened with the climate based on what's in the rock itself and also the chemistry and physical conditions of the rock. So here, for example, we have this limestone, which means a relatively stable climate, these white layers. And this is an interval where we have a big anoxic event, a big warming event in the climate, and it creates this black shale. And then it finishes and we go back to our normal conditions. So we can look at rock records like this, stratigraphy it's called, or the layers of the rocks, to tell what's happened in past climates. Now, there's a number of different ways we can do this. The rocks themselves record the processes that have shaped them as they were deposited. So, for example, we can see evidence of ice from things like drop stones. And this is a rock that's fallen out of an iceberg, gone through the ocean and dropped in the deep sea. And so when we see these preserved in the rock record, we know that there was ice around. Similarly, when we see reefs, we can generally assume that these are tropical structures that grow in the tropics. They have beautiful textures and crystals that precipitate from these reefs that can tell us about the ocean chemistry and the climate at the time of the reef growth. Things like salt crystals can tell us about that maybe there were salt flats, maybe this was an arid climate, so something like Central Australia. And of course, then we can use fossil animals and plants as well to tell us about this climate history. We can analyse the different parts of the shell, for example, or the organic carbon that makes up the plant to tell us about the past climate. So there's a number of different ways you can do this using the rock record. So the work that I do, just as an example, looks at ancient reefs that are about 600 million years old. So this is around about the time that animals evolved. And here is one of these reefs. It's this grey layer in these big mountains in Canada. And we hiked up this little valley, and you can see on the right here that my colleague Malcolm is measuring the distance or the thickness of the rocks. And as we go, we record what's in them, and we take samples back to the lab and look at them to analyse the chemistry and tell us about these ancient climates. So this is just an example of one of the techniques we use in geoscience to look at past climates. Okay, so a bit of background, but now I want to really focus on what controls this long-term climate. How has life been able to evolve on our planet? How has our planet been able to have this relatively warm and stable climate through its history? And this is, of course, a photo from one of the Apollo missions, which nicely shows the Earth, I think, as this oasis in space, like NASA put on their poster. Okay, so stepping right out for starters, there's this idea of the habitable zone around a star. So essentially the broadest control of the climate on a planet is its distance from the sun, or its distance from the star. And of course, it depends on how hot the star is. And so too close to the star, places like Mercury and Venus are too hot to support life. Water just boils away, essentially, from the planet. Mars, even though this diagram has it within the habitable zone, probably is right at the very outer edge of the habitable zone. It's too cold, really, to support liquid water. There's only ice on Mars. And so this habitable zone, or the Goldilocks zone, it's sometimes called, is the area, essentially, where you can have liquid water on your planet. And so the heat from the sun is essentially what is the main control on Earth's climate. So for example, Venus is too close to the sun, it's too hot. Its surface temperature is about 460 degrees Celsius. These are two pictures, some of the only pictures we have of the surface of Venus. Russia sent some rovers there in the 80s and 90s, and they only lasted for about 2 hours before they just melted. And so these are photos taken under this atmosphere that's about 96% carbon dioxide. And what happened was basically as the sun got brighter through its history, Venus may have had oceans, but these oceans have essentially boiled, and its atmosphere is like one dense, extreme carbon dioxide rich ocean in a sense. So not really great for supportive of life as we know it. On the other hand, Mars is too far away from the sun at present. It's too cold. The average temperature is something like -65 degrees Celsius. And this is a photo taken from the Perseverance rover. You can see the little Ingenuity helicopter taking its first flight on another planet. So Mars may have had water in the past, and that's what they're looking for in this area, this Jezero crater of Mars. But at present, it only has water locked up at ice in the poles, and it's really too cold to support life. So complicating this idea of the sun controlling climate, solar luminosity, or the heat that's put out from the sun, has not been constant through time. And so the sun, or stars like the sun, main sequence stars, evolve over time, over billions of years. And essentially our sun is getting hotter as it goes through time. And you can see this on this axis here. So this is from the start of the solar system all the way through in billions of years to when the sun might explode or something terrible will happen. But it's billions of years in the future. We don't have to worry about it. Here we are at about 4.5 billion years after the sun began. And it's gotten about 30% brighter. Or in the other way around, the sun back in the early part of the Earth's history would have been about only 70% as strong as it is now. So the habitable zone is much more complex than just the distance from the sun. It evolves over time. And this sets up this paradox that's been known in earth sciences for quite a while, called the faint young sun paradox. And it relates to this weak sun in the early Earth. How, if the sun was weaker than it is today, how is it able to support liquid water on the surface of the planet? And how has it maintained that through, as it's gotten warmer through time? And so we know that, as I said, we know that there was liquid water on the early Earth. We can see that in the rock record. This is an example of a rock that's been transported by water from the very early Earth, from South Africa. And it's rocks like these that we can use to reconstruct this history of liquid water. And we know essentially that this has been the case through Earth's history. So how has this happened? How are we able to support life through this period of time? So I'm just going to go through the reasoning behind this faint young sun paradox and then present a kind of solution to it. So on the left here, so on this axis, we've got time, so 4.5 billion years up until today. And this graph on the left has got solar luminosity, so the strength of the sun. And so back in the day, it was only about 70% as strong as it is today. And right up here at today, it's at the same value. On this graph, we have the surface temperature of the Earth in two different cases. So this first line here shows how hot the Earth would be without any atmosphere. And you can see back in the early history, it would have been like -40 degrees at the surface. And today it would only be about -25 degrees if we had no atmosphere at all. So not warm enough to support liquid water or life. This line here is if we had our current greenhouse atmosphere. So over here, you can see that our current surface temperature is around 15 degrees Celsius, and we have about a 30-degree greenhouse effect from our atmosphere. So if we had with our current atmosphere through time, along with the strength of the sun, this line gives us what the temperature of the Earth would be. And you can see that back in the early Earth and through most of Earth's history, up until about here, we would have had a frozen planet. So our current greenhouse atmosphere isn't enough to have warmed the early Earth and to keep Earth habitable through its history. So what does that mean? How can we answer this? The simplest solution to this problem is that the atmosphere has changed through time. So in the early Earth, we had a much more carbon dioxide rich atmosphere, much more greenhouse effect, a stronger greenhouse, to compensate for this solar radiation being relatively weak. But today, we have a much weaker greenhouse atmosphere, less CO2, and that CO2 has been locked up in the Earth itself. And this is kind of thought to be the simplest solution to this paradox, faint young sun paradox. And so there's a lot going on in this diagram, but I just want you to focus on the bottom here. So this gray area is a really rough estimate from Eisen and Plansky and other people like James Casting of CO2 through time. So we've got here, I've put roughly the amount of CO2. So today's atmosphere up until about 30% of the atmosphere being CO2. And we go from about 4 billion years all the way through to present. These dark blue bars give you the big ice ages that we've had in Earth's history. And so we kind of get our estimates, our models and proxy evidence, which is all, has its own caveats and flaws, suggests that this early part of Earth's history is characterized by very large amount of CO2 in the atmosphere. And that has gradually declined through time. And in the later part of Earth's history, we have some of these big ice ages, which are associated with big events in Earth's history. So this snowball Earth is a time that the Earth is thought to have frozen almost solid. And that's associated with the evolution of animals. And this big ice age here in the Paleozoic, about 200 or 300 million years ago, is associated with the evolution of land plants. But essentially, what I wanted to show just with this diagram is that the CO2 content of the Earth has changed through time. And it's a planetary process that controls this atmospheric composition over this billion-year timescale. So essentially, to summarize that kind of faint young sun paradox, Earth's climate is more complex than simply being in the right place at the right time, the Goldilocks zone, habitable zone. It's actually, we need this atmospheric composition to regulate our stable climate on Earth, to keep liquid water on the surface. Okay, so this takes us then into carbon cycling and how this long-term Earth controls climate via the transfer of carbon between different reservoirs. And so you might have seen the short-term carbon cycle, it's often just called the carbon cycle, in school, for example. And this diagram kind of shows the storage of carbon in these different reservoirs. So we think about in the short-term surface carbon cycle that we think about that regulates our short-term, our current climate, for example, in terms of hundreds or thousands of years of climate change, it's related to the transfer of carbon as CO2 in the atmosphere, as carbon dissolved in the oceans, carbon in soils and in vegetation. And all of these reservoirs transfer carbon around them and cycle it through them. And that's what regulates the amount of carbon in the atmosphere. And so these, if you look at the numbers underneath these numbers here and these percentages of the total carbon of the Earth, you can see that these surface reservoirs are really very, very small compared to the Earth itself, which has 99.9% of the carbon held within the rocks and the inner planet of the Earth itself. So the Earth is actually the biggest reservoir of carbon. And it controls this long-term carbon, because like carbon is cycled between the ocean and atmosphere and vegetation, carbon is also cycled in plate tectonics. As the Earth recycles itself, carbon is transferred between these different reservoirs. So it's these geological reservoirs that we consider to control long-term climate stability. And the most of the carbon locked up in these sediments is in the form of limestone, which is calcium carbonate, and organic carbon in things like shales and coals and the stuff, fossil fuels, essentially. This is where most of the carbon in the Earth is held. So I've just put this up, essentially the same thing I said here, with little pictures of these rocks. So most of the Earth is made up of what we call silicate rocks. They're rocks that have silica in the structure. These are things like granites and bluestone basalt. These green crystals are probably what the inside of the Earth looks like, which would be very nice to get down there. But most of the carbon within the rock record is held in coals like this one from Victoria, and shales, which have a lot of this organic matter which happen in the deep ocean. The kind of link, I guess, between the rocks and the oceans, so the deep carbon reservoir and the surface ones, are calcium carbonate or limestone rocks that form in the oceans. So these are things like reefs or shells, and these precipitate from the oceans, and they are a way of taking carbon from this surface reservoir and putting it into the rock, so that they take up part of this long-term carbon cycle, which I'll go through in a bit more detail. So that's how carbon is stored in the Earth. So essentially, to summarize that, I guess the ocean atmosphere biosphere, so plants, soils, the atmosphere in the oceans, controls this short-term climate, so over hundreds or thousands of years. But most of the carbon that we have in the rock record is held in these sediments, like things like coals and limestones that have carbon in their structure. And if we think about long-term changes to the carbon balance between these reservoirs, it's really about removing or adding CO2 to the atmosphere or oceans from the rocks. And so we're doing this, humans are doing this now. We're taking fossil fuels and releasing them directly into the atmosphere. And that's what's accelerating our current climate change. But there are geological processes that also do a similar thing, but over much broader timescales. So this comes down to this plate tectonic theory of the Earth. And hopefully this is something you would have learnt about a little bit at school. And essentially what it is that the crust of our Earth, which is kind of like the thickness of the crust of an apple, skin of an apple, is cold. And the heat from the center of the Earth, as it cycles through the inner planet, it comes up in some areas and it gets warmer, and this creates the rifting, or the crust to rift apart, essentially. And as this crust gets colder or hits into other bits of crust, it then subducts or goes back into the Earth as it cools. And so it's like a cycle of heat, essentially. And this cycle of heat is moving our crust around. It's moving our continents, so things like continental drift. It's creating our mountain ranges when these bits of crust hit together. And the processes that are involved in plate tectonics are the processes that control this long-term carbon cycle. So we have, for example, in our oceans, we're forming these limestones. these limestones, as this heat transfers, these limestones are going down, down, down into the center of, or towards the center of the Earth. At a certain point, they melt, they come back up, and they come back up as things like volcanoes, which emit CO2 into the atmosphere. And the rocks on the Earth erode and they weather and they're transported back into the oceans and they form the limestones again. And so this is this this long-term carbon cycle, which I'll go through in a little bit more detail. That's reliant on plate tectonic theory. This is our current arrangement of continents. These red ones give you the areas where we have rifting, where the oceans are rifting apart. And these green areas here, notably around the Himalayas, are where these continents are colliding together and creating big mountain ranges and big volcanoes. So you might have heard of like the Ring of Fire. But the arrangement of our continents today is not always how it has been in the past. This is an example from the end Mesozoic. This is the extinction that killed the dinosaurs around 65 million years ago. This is where the asteroid hit these poor dinosaurs here. And this is what the planet looked like. And you can see that at this point in time, Australia would have been much colder down towards the South Pole. India is moving up this way and it hasn't formed the Himalayas yet. So a very different kind of time. And at this point in time, actually, with the asteroid impact, we get one of these really big climate change events. This asteroid hit this kind of tropical seaway and vaporized a lot of the rock, which would have led to short-term cooling, but probably then thousands of years of warmer temperature after the impact. So just an example of one of these big climate change impacts on Earth. Okay, but getting back to the carbon cycle, I'm getting distracted by dinosaurs. The first part of this long-term plate tectonic geological carbon cycle is called silicate weathering. And so I mentioned that the Earth is mainly made of silica minerals, silica rocks, and here's an example of one of them, chemical formula. And what happens in this first part of the cycle is the CO2 in the atmosphere combines with water, with rainwater, and it makes a really weak acid called carbonic acid in the soils. And what that does is it weathers or erodes the rock, physically and chemically erodes the rock and dissolves it up into little bits, and it transports these bits of calcium, of bicarbonate, silica that were in this rock, and they transfer them into the oceans. So it's a way of breaking down the rocks and moving them into the water. When it gets into the water, when these elements get into the water, they combine to make limestone, things like plankton shells, for example, and silica. And these are also made up by animals, things like diatoms. So the first part of this equation is the addition of CO2 and the rock, so weathering of the rock with CO2 and water, and transferring it into limestones, essentially. So this is a way of removing carbon from the atmosphere and putting it into rock. Okay, the second part of this equation is essentially the same thing in reverse. So we're taking this rock that we made in the oceans here, and we're subducting it down into the earth, melting it, and pushing it back up through volcanoes and metamorphism. And so this second part of the thing takes the rock, basically, and over a very long time period, releases it back into the atmosphere. And this forms the two sides of this big long-term carbon cycle. So I've just got a schematic of that whole thing put together now. So I'll just go through it again. So we have the CO2 in the atmosphere combines with rain, weathers these rocks. So this process of weathering where we erode, chemically and physically erode the rocks, and we put runoff and rivers, they dump these things back into the ocean, where they form limestones. And so over very long periods of time, probably millions to hundreds of millions of years, these limestones are then subducted, melted, and released again from volcanoes into the atmosphere. And this is kind of neatly summarized by this very simple equation. And so this is what really over hundreds of millions of years controls the climate. I should just put, these are two of the main papers that go through this long-term carbon cycle. This second one here by Walker et al. Looks at a negative feedback within this cycle. That is the main process that I'm going to go through now that regulates this long-term climate. So that involves the weathering component of this cycle is related to climate itself. And so I'll go through that. And what this does is help stabilize its long-term climate via this cycle. So I mentioned that this weathering process is controlled essentially by the climate at the time. And this might sound a bit tricky, but I'll go through it. So this is a graph of temperature and latitude. So this latitude of 0 being the equator. And we know that at the equator, where it's warmer, we get more sun radiation. Where it's warmer, it's also wetter. So we receive a lot of rainfall here. We have higher temperature. And in this area, we have more weathering. So wetter and hotter climates are much more adapted at weathering rocks. And so in this case, in the silicate weathering, we're taking the CO2 in the atmosphere and taking more of it and transferring it into these limestones in the ocean. So when we have a warmer climate, it means that more carbon dioxide is removed from the atmosphere. And we have vice versa. So when it's a colder climate, we don't have as much weathering, and so it's harder to get CO2 out. And what this does is it acts as a stabilizing feature on the Earth's long-term climate. So I'll show you what that looks like in a little diagram. So this is called the silicate weathering feedback. So for example, we have some change in the system, say humans burning fossil fuels, which leads to a warmer climate, which then leads to, like in the tropics, increased weathering, increased removal of CO2 and putting that through rivers back into the oceans. Increases chemical weathering, removes more CO2, and what that does is it cools the atmosphere. We've taken out the greenhouse gas and it reduces the initial warming. And it's the same thing in reverse. If we have a slightly warmer climate to start with, we get less weathering, we take less CO2 out of the atmosphere, and it causes a reduction of the cooling. And this operates over millions of years. So this is often like a 100 million year cycle. So this is not going to save us from our current climate crisis anytime relevant to humans, but it will eventually stabilize the Earth. And essentially this silicate weathering feedback, which reduces any initial kind of perturbation to the system, is Earth's thermostat. It's what keeps our climate stable over very long time periods. And it's what explains how we can have liquid water on our planet through Earth's history. We essentially had much more carbon dioxide to start with. And as we've gone through, we've removed that carbon and put it into the rocks, just so we can balance the sun, essentially, over very long time periods. And there's a couple of complicating factors that I'm not really going to go into, but I'll just mention. So for example, if you have mountains like the Himalayas, you have much more weathering because you're taking those rocks and you're putting them up really high where they're exposed to a lot of weather, essentially, a lot of rainfall and stuff like that. So when you have big mountain ranges, you erode and weather rocks, which leads to cooling, which leads to the removal of that CO2. And when you have rocks, places like Indonesia, where you have volcanic rocks, which are really reactive to weathering, to rain, things like these green minerals, they are also really good at cooling the climate because they take that CO2 and more rapidly transfer it into the oceans. So when you have, for example, if you have a time in Earth's history where you've got a lot of mountains, or you've got a lot of island arcs, which are these volcanic kind of tropical islands, this is times where you get a lot of cooling in Earth's history. And so essentially it all comes back to then plate tectonics and the arrangement of the continents. Which parts of the rock, which continents are in the right spot to change the weathering system. So when we have, for example, a lot of equatorial continents, so not necessarily like today, but in times in Earth's history, we've had a lot of our continents spread over the equator. In these times, we expose these continents to a lot of rainfall and high temperatures. And you can see in dark colors here, this is on our modern Earth, where we have the biggest amount of rainfall. And these are the rocks that weather the most easily. So times in Earth's history when we have equatorial continents leads to cooler climates, leads to CO2 removal via weathering. And the opposite is true when we have climates at the poles, we have less weathering, and so forth, we don't take as much CO2 out. And so I'm talking about this is over millions of years timescales where we're moving the continents very slowly across the Earth, and it's slowly re-stabilizing the climate every time they move. Okay, and that leads to kind of just going through some of these events in Earth's history now that we kind of understand properly how this carbon is cycling over long timescales. I want to go through now some little events and how they have changed climate in Earth's past. So for example, I mentioned equatorial continents receive a lot of rainfall and create a lot of weathering and draw down CO2. When we have continents all stuck together, so these are things called supercontinents. You might have heard of them also maybe from school. These things happen maybe 4 or 5 times through Earth's history. We get all of the continents that drift and get stuck together. So here's an example, Pangaea or Gondwana you might have heard of. These are big land masses and the rest of the Earth is just ocean. So there's 2 of these in recent Earth's history, the last billion years. Pangaea is one of them, around about 200 million years ago when the dinosaurs were around. And Rodinia is one about 1 billion years ago. And this is just before the evolution of animals. And so what happens when we have all the continents stuck together like this, and you can see an example, like if you look at the weathering or the rainfall around Australia, all of the edge of the continent has rainfall and is exposed to oceans and ocean currents and can weather a little bit. But the inside of the continent, like the desert in the middle of Australia, is really dry and arid. And so when we have this on a global scale, the interior of these big continents being dry, it leads to overall, on the Earth scale, less weathering. And so less of that CO2 is being transferred from the rain into the oceans and into the rock record. And what this does is leads to these really warm climates. And so this is, classic. You think of the dinosaurs, you think of them hanging around in tropical rainforests, like in the Jurassic Park movies. This Pangaea continent would have been very warm. This is a warm period of Earth's history. And of course, when these continents break up, that's when the cooling starts. So this happens over, as I say, hundreds of millions of years. So now this is, again, a complicated diagram that I don't want you to pay too much attention to, but I just wanted to show it because it has in these blue bars here some of the Earth's glaciations or ice ages that have happened in the last billion years of Earth's history, let's say. So this is time on this axis going from 700 million years ago to today. And so the things that people have focused on a lot in research and the work that I look at is around this snowball Earth period of time. And this is when we have a big continent that's breaking up, this Rodinia continent that's breaking up, and it causes a massive ice age. We have a relatively warm period after that for the next couple of 100 million years. We have another ice age, which is associated probably with the evolution of plants. And then we have, again, when this Pangaea big continent forms, we get a hot period, which is when the dinosaurs were. And as that begins to break up, we go back into another ice age. So this is this cycling effect of the movement of the continents, creating this sort of cycling of the climate on Earth over long periods of time. Okay, so snowball Earth. So this is one of the biggest ice ages, the coldest ice age in Earth's history. And it initiated just as this big supercontinent Rodinia broke up. So this continent formed about 1 billion years ago. And here we are, this is a map of the Earth, what it's thought to look like around 700 million years when this continent starts rifting apart in different directions. And because you can see all of these continents are at the equator, that means that suddenly, instead of having one big lump of a continent that's arid on the inside, you move all these little pieces apart. And as you do that, each of them has its own little coastline that receives a lot of rainfall. And that increases weathering a lot. And it's thought that a lot of these rocks formed big mountain ranges and they were made of reactive rocks, like places like Indonesia today. And so what this does was created this runaway drawdown of CO2 as you've taken that CO2 out of the atmosphere and transferred it into the oceans and into rocks. And this rifting event, these equatorial continents, has caused what's called snowball Earth, where people have hypothesized that perhaps the whole oceans and whole Earth froze. And my research kind of shows perhaps more of a nuanced history of this, but certainly this was one of the biggest ice ages in Earth's history. So there's 2 of these events, one that went for about 57 million years and another one that went for about 5 million years. And in the middle of this period of time, we get these big tropical reefs that I work on. So it's a very crazy period in Earth's history in terms of climate. And the idea that this is the idea that the Earth's thermostat broke to get yourself into a snowball state. We recovered. So there's good news. We can always recover. The Earth always seems to recover from these events. But what happened was, because of this cooling induced by the breakup of this big supercontinent, you start getting ice forming. And when you get ice forming on the Earth, you then have more sunlight that's reflected. That's the albedo of the planet. And as you reflect more and more sunlight, you get more ice, and eventually you can get yourself into a state where the whole thing freezes solid. And but the way that we got out of this is also related to that same long-term carbon cycle. So although it's frozen, the same reaction here that I was showing you about the long-term carbon cycle still holds. So while it's totally frozen, we don't have any rainfall, we're not weathering any material into the oceans. In fact, we think our oceans are covered with this big ice sheet. So nothing's getting into the oceans. However, we're still having volcanoes, we still have plate tectonics going on. And what that's doing is taking the carbon that's in the Earth and then re-releasing it into the atmosphere. So eventually, the idea is that the CO2 in the atmosphere builds up to such a point, such a greenhouse effect, that it just melts all the ice over perhaps thousands or millions of years, probably millions of years. And so this is one of these events where this thermostat sort of potentially broke, but it got better. So this long-term carbon cycle is regulating it to get us out of events like this. So that was the Snowball Earth event here. And there's another one of these glaciations around the time of Gondwana, the continent Gondwana. And just to end, I just wanted to show you a couple of slides of this ice age that we're in at the moment, the Cenozoic ice age, associated with the breakup of this other big continent, Pangaea. Okay, so we've changed axes here. So we've gone from, this is around 70 million years ago. This is what the Earth would have looked like around about this time. This is the same time that we have the asteroid that kills the dinosaurs. And as we go up on this axis, we're going through to current day. And what this curve is showing is a rough estimate of global temperature through time. So in the early part of this record, around the Eocene it's called, we had very warm climates. We didn't have really any ice. We had things like hippos and lemurs and crocodiles hanging out in places like Greenland around about this time. So very greenhouse world. We have this one big climate event called the Paleocene-Eocene Thermal Maximum, or the PETM. And this is a big release of methane into the atmosphere that causes a very short-term climate event, climate warming. And this is one of our most recent analogues to our current climate change, because it's very rapid. But from this point, as we go through to today, we essentially go through this cooling, or this long-term cooling of the Cenozoic. And essentially, as I say, it's driven by these tectonics, these plates rifting apart, the big supercontinents rifting apart. As it's rifting, you have more weathering of the continents, draws down the CO2, puts it into rocks. And there's lots of arguments about exactly what caused it. And one of the big ideas is that it's related to the Himalayas actually forming. So this related to this big mountain range forming that enables more weathering and more CO2 to be drawn down. So the Himalayas are thought to have India is thought to have drifted north and hit Asia around about 50 million years ago. And that's exactly when this start of the cooling occurs. We don't get the Antarctic ice sheets until around about 34 million. But this is a picture of the Himalayas today. So a really massive mountain range. And we've got things like monsoons, which have a record back to about 24 million years ago. And these monsoons are a big event where you introduce a lot of rainfall, you have a lot of weathering. You've got these rocks up really high. If anyone's been to the Himalayas, you can just see things absolutely shedding off, and there's huge rivers coming off. This is a method of removing that CO2 from the rain, from the atmosphere, into rivers and then into the oceans and making limestone. And this is perhaps a very long-term cooling effect that is helped by things like big mountain ranges being uplifted. So potentially the Himalayas is one of the impacts that's caused our recent ice age. And of course, there are much shorter term climate fluctuations in the time that we're in now. So if this is, for example, looking at the CO2 concentration through time from the last 800,000 years. So now I'm a geologist, obviously I'm saying this is very short term. This is still long term compared to humans. And you can see the cyclicity in our ice age, or in these ice sheets, are often called glacial interglacial cycles. So between warmer and colder parts of this history, this cyclic process is also caused probably by slight changes in our solar radiation. And that's because things like Milankovitch cycles, which you probably have looked at a little bit, or maybe could look into if you're interested. These result from changes in the Earth's orbit and the way that it spins and the way that it's kind of pointing towards the sun. So these are small scale changes in the Earth system that are also caused by the sun, essentially. So really, we've got the sun to thank for a lot of this stuff, and the Earth to thank for the rest of it. So yeah, I just wanted to put this up as an indicator that I'm not totally ignoring these smaller scale changes, but just showing that there are really big changes in Earth's climate that have happened through Earth's history. And you can see that our CO2 today has gone way off the charts of any of these scales that I've been talking about in this lecture. So just to finish, I just wanted to put this in perspective. So this long-term Earth history, we have a lot of crazy CO2 levels in the past. We have crazy climates where we've frozen the Earth and thawed it out. We've had a lot of big changes. But really, our current climate change is the most rapid change in CO2 and temperature that we've ever experienced on the Earth. And so this is a table that Andrew Glikson has made from his book. And in this table, he shows several of these events. So the impact that killed the dinosaurs, this big methane release event that are in the warm period that I showed you, the last glacial termination, and our recent warming. And if you look in these two columns highlighted in orange, you can see that our current warming rate, is an order of magnitude higher than any of these events, including an asteroid that killed the dinosaurs. So pretty extreme that we can compare our current warming to things like mass extinction events. And again, the CO2 change that we have today, 0.44, is more than twice what we had when we think we killed the dinosaurs. So pretty alarming in terms of, I think when you know a bit about Earth's history, you become a little bit alarmed about our current climate change. But there are things, of course, that we can do about it. Humans are very clever as a species, and we definitely are relying on everyone, including you guys, to come up with solutions to this. And there are abundant solutions out there. It's just a matter of us being able to implement them and really make a change. So I'll finish there. I've basically summarized already. Long-term climate controlled by geological processes, and silicate weathering feedback is what stabilizes it. And you know, although things have changed in the past, they've never changed this rapidly. I put up some references here if you're interested in learning a bit more. And if you are interested in learning more, there's some subjects listed down the bottom there, particularly past climates that we teach in our school that go into this in a lot more detail. So thank you very much for listening.
Thanks so much, Ash. I think that really helps contextualize the recent climate change we've been looking at in this subject. But at least for me, I find it very hard to wrap my head around the timescales of millions of years. But yeah, it's super interesting. Thank you. So we have a little bit of time for question and answer. So if you've got any questions, just feel free to put them in the Q&A down below. I might just ask a fun question to begin with. So you showed some pictures from your fieldwork, I think on like your second slide. Where is your favorite place to do fieldwork?
Ooh, that's a good question. I mean, there's so many good places. So I've done a lot of work in Africa, in Namibia, and that is really beautiful, beautiful deserts, amazing people. It's like just a really lovely place, and beautiful rocks, I should say. But I mean, Central Australia is amazing. This picture here that I've got up is from Canada, and that is field work. You get put in by helicopter, and you're kind of abandoned to camp and walk up these big mountain ridges and try to figure out what's going on. And last time we went there, we got chased up by bears. So, but yeah, definitely, if you're interested in learning more about in fieldwork and stuff, this get into it, get involved.
Yeah, I think I mean, there's lots of areas of science that involve fieldwork, but geology is certainly an area where there's more fieldwork opportunities, including in some of these subjects. You've highlighted a couple there as well, the geology of Southeast Australia and Earth's surface processes. I'll ask, well, so I do see a question about how this relates to the assignment, which I'll just answer briefly. So Ash has just given a really nice overview talk of kind of the controls on Earth's long-term climate. I will pose an assignment question based on this to do with this talk, and you'll write a short essay about the question, answering the question using Ash's talk as one of your references. So the recording for this talk will go on the LMS site later today as well. So yeah, please continue asking any questions you have. I'll ask just a follow-up question. So I learned quite a lot because I don't really focus on long-term climate changes. I was just wondering, given the direction of the movement of continents at the moment, would we expect more weathering in future? So would we expect this weathering process to continue speeding up?
I think as we go through, I think the next supercontinent is predicted in about 200 million years from now. So pretty far in the future. But we do have quite a few continents at the equator today. But it looks, if you look at the way things are moving, I think Australia is due to crash into Asia and America is due to crash into Asia as well. So as they move, they'll probably move further north and move away from the equator. So likely the cooling will slow down and will come out of this. I call it an ice age. Of course, it doesn't feel like an ice age. It's just in terms of relative to the rest of Earth's history. It's relatively cool. But yeah, so hopefully when this next supercontinent forms, it'll just stabilize everything again and sort out and warm up a little bit. But yeah, as I say, like these big extinction events, it's really related to the rate of change. There's a couple of these big extinction events in Earth's history. They're all related to climate change on very short timescales. The one that killed the dinosaurs, for example, wiped out about 70% or 75% of life on Earth. So hopefully we can avoid that this time. We're relying on you guys or all of us really, to solve it.
Yeah, we'll be talking a bit more about solutions to climate change next week in this subject. There's a question. Well, so firstly, there's a question about the length of the essay. All the details about the essay will be available soon. So in the next few days. But it's under 1,000 words. I actually can't remember the exact word count, but it's not very, very long. There's another question here, and it's something I was thinking about as well, is these time estimates. Like they are quite vague, and there must be some uncertainty on them as well.
Yeah, that is a very good point, and I didn't go through that really in a lot of detail, but that's very true. Essentially anything in the Earth's record of early Earth and the record of probably most of Earth's history is pretty vague. There's because of this process of plate tectonics, where you recycle the rock, we don't actually preserve much of the ancient Earth. So places like Mars, where they don't have plate tectonics, they've preserved exactly all of the rock through all of time. But because we remove that rock, we only get these little windows of certain parts of that history. And so, for example, this place I'm showing you in this photo, I'm standing on about 600 million year old things, and they go up to about 400 million. But there's gaps in that record as you go through these different layers, there's big gaps. And the way that we date these rocks is also full of uncertainty. So you can date the rocks using minerals, using things like uranium lead decay schemes. And that gives you a really precise age. So it might be like, this rock is 605.47 million years old. But a lot of the time we don't have these minerals that can record this. So we rely on other indirect methods to date the cycles. And so, and so that's true that there is a lot of uncertainty in these big processes. But when you're talking about things that happen over 100 million years, the error doesn't have to be, like the error can be of that order of 1 million years or so as well. When you're looking at things like these interglacial glacial cycles, or even in the Holocene, the most recent part of Earth's history, that the climate changes, you want to have much more precise dates on those things. And we do. So as you go further to in Earth's time, you get much better control on the exact ages of different rocks, for example.
Thanks, Ash. That makes sense. So there's one final question that's about the grading of the essay. So you will get a grade on the essay, but you have to achieve at least 50% on the essay to pass this hurdle. Again, there'll be more detail and instructions in the next few days. So for now, let's thank Ash again for this really nice talk, really nice overview covering a lot of Earth's past, and really complements what we've been discussing in terms of recent climate change in the subject. So we'll wrap it up there. I'm going to stop the recording. Thank you all for attending. The recording will be available soon on LMS. I'll post an announcement about it as well. And I'll see many of you later on today at the lecture as well. Thank you.
Thanks very much, everyone. I hope it wasn't too much stuff all in rapid succession.
It was good.